So in the last video we said that petrol burns like this and diesel burns like that, and we know why. In this video we'll talk about vehicles, fuels, and after treatment of exhaust gas. To be honest, I'm making this video for my super curious E-level student, but I also put a bunch of things that are not at E-level. So please take a look at the map to decide whether you want to watch it. So talking about fuels and vehicles really comes down to combustion in an engine. This is a broad and complex topic, but we are going to mention only three things: the design of the engine, the property of the fuel, and pollutants. Just to say, I'm not an engineer, I study chemistry, so although there are many types of engines, we'll only mention two types: petrol and diesel engines commonly found in cars, which are 4-stroke piston engines. When it comes to fuel, again, there are many things that need to be considered. For instance, how easy the fuel ignites and how much energy it gives off and so on. Just notice diesel is slightly denser than petrol, so it means that you get a little bit more energy per liter. So let's start with pollutants. The most obvious is carbon dioxide. In reality, you will never be able to burn all the fuel completely, so there will be some products of incomplete combustion. I'm sure you know about carbon monoxide, but there are also hydrocarbons abbreviated as CH. You see, some of them are alkanes, mostly having 1 to 3 carbons, but there are also unsaturated species like ethene, ethine, so yeah, CH covers all. So what are the mechanisms that lead to these products, you ask? The short answer is that the mechanisms are very complex, nothing that you should or want to learn by heart. To demonstrate that, let's take combustion of methane. The equation shows that 1 mole of methane reacts with 2 moles of oxygen, assuming complete combustion. It doesn't mean that methane molecule collides with 2 molecules of oxygen in a single step given carbon dioxide and 2 molecules of water. There are many steps, in fact approximately 200, that is, 200 elementary reactions, and the mechanism is mainly radical in nature. Complex reaction paths for combustion means that there are many products possible when there is not enough oxygen around. Some products of incomplete combustion are partially oxidized, so in an exhaust gas you will find molecules like methanol, ethanol, or propanone. Volatile organic compounds that leave the exhaust are called, surprise surprise, volatile organic compounds, VOC. Why should we care? Well, VOC plays a big role in formation of photochemical smog. Speaking of smog, nitrogen dioxide and nitric oxide, which we'll talk about in a second, also contribute to the photochemical smog. Anyhow, next we have particulate matter, PM. Particulate matter is defined as solid and liquid particles suspended in the air. Particulate matter from car exhaust is soot, which is often thought to be the most complex of exhaust emissions. So let's look at this diagram. So fuel and oxidizer come together, small radicals are formed, and in absence of sufficient oxygen, these radicals form small molecules with aromatic rings, which then form bigger aromatic molecules. These are called polyaromatic hydrocarbons, PAH. Polyaromatic hydrocarbons are composed of multiple aromatic rings. Most of them look like fused benzene rings. So now we are going from molecular zone to particle zone, and then coagulation leads to the final soot particles. What is the most disturbing is that many PAH molecules are cancerogenic. They were first linked to cancer in chimney sweepers in the 18th century. Interestingly, it was the first reported form of occupational cancer. Nitrogen oxides are created due to combustion in an engine. Why? Nitrogen oxides formation is endothermic and temperatures in an engine can easily reach 2000 Celsius. So let's first use the Chatelier principle, or whatever that is pronounced. So the principle is telling you that it will disturb the system by changing temperature, pressure, concentration, then the system will respond in a way so that to minimize the disturbance. If we increase the temperature, according to the Chatelier whatever principle, the system will try to decrease it again, in our case producing a bit more of nitric oxide. If you are undergraduate, then the Van Hoff equation might ring a bell. So this equation tells you that increase in temperature will result in decrease of equilibrium constant for exothermic reaction, but in increase of equilibrium constant for endothermic reaction. Anyway, so let's do some calculations. So we can see that even at 2300 Kelvin, the equilibrium is much less than 1, which is consistent with getting relatively small amount of nitric oxide. So this equation is E-level stuff, only that the equation is quadratic. So if you want to have a go, then pause the video now. Okay, so first we get the number of moles. Then we notice that if Z number of moles of oxygen is consumed, that means 2Z moles of nitric oxide is produced. So if you are in high school, then you would calculate Kc by using concentrations or Kp by using partial pressures. But let's notice that the number of moles on the right hand side and the left hand side are the same, so we can simply use the number of moles in the equation. I don't really want to dwell on details, I will soon make a video on equilibrium constant. Just remember that Z is the number of moles, so it cannot be negative. And then the last step, number of moles of nitric oxide is 2Z over the total number of moles at at equilibrium, which is 0.3, and we got 1.6%. Notice that the question said that the mixture was allowed to come to equilibrium. It turned out that in an engine, the reaction O2 plus N2 is too slow to account for all the nitric oxide produced. Remember that thermodynamic parameters like Gibbs energy or equilibrium constant, they can tell you how much product you are going to get. Nothing traces a lot, but it doesn't tell you how fast the reaction happens. It is the kinetic parameters that tells you how fast. So although the reaction O2 plus N2 is very simple and that is the reaction that you will find in E-level books, scientists had to come up with some additional mechanisms to account for all the nitric oxide present in the exhaust. And if you want to find more, use keywords extended Zeldovich mechanism. I'm so bad at pronouncing those things. Anyway, that should give you at least a good start. And by the way, the mechanism, not surprisingly, involves radicals. In fact, there are three oxides that are most relevant to combustion: nitric oxide, which dominates, much less of nitrogen dioxide, and almost traces of nitrous oxide. We just said that nitric oxide and nitrogen dioxide contribute to photochemical smog. Moreover, nitrogen dioxide is very harmful to respiratory system, causes eye irritation, and so on. Nitrous oxide, laughing gas, is not good either. It is said to be 300 times more powerful greenhouse gas than carbon dioxide. Then we have the pollutants due to impurities in the fuel itself. Here we have sulfur dioxide, which comes from oxidation of sulfur present in the fuel. Nowadays, it's not that much of a problem because fuel undergoes desulfurization. Then we'll briefly talk about treatment of exhaust gases. So in petrol cars, you need three-way catalytic converter, TWC for short, and we are pretty much done. In diesel, there is diesel oxidation catalyst, DOC, diesel particulate filter, DPF, and selective catalytic reduction unit, SCR. So diesel has a bunch of things, and to appreciate why is that, we need to see how these engines work. So 4-stroke engine does 4 strokes to complete a cycle. This starts with the intake stroke, where the piston descends sucking air into the cylinder through the open intake valve, followed by the compression stroke, where the valve closes and the piston goes back up, followed by the power stroke, where the piston is forced back down by combustion, and the final stroke is when the mixture is pushed out of the cylinder through the exhaust valve. So intake, compression, power, and exhaust, or if you prefer, suck, squeeze, bang and blow. Anyhow. And when I said piston is forced back down by combustion, what I really meant is that combustion increases the temperature, and that increases pressure, and the increased pressure pushes the cylinder down. Now let's talk about differences between diesel and petrol engines. The main difference is that in petrol engine, the piston compresses fuel-air mixture. The fuel is delivered to the cylinder in the first stroke, the intake stroke, whereas in diesel, the piston compresses air only. Before we go into the second major difference, we need to appreciate what happens to the temperature when gas is compressed. Well, the temperature rises because the compression in the internal combustion engine can be treated as approximately adiabatic. I know it might sound a bit dry, but let's get on with it. So adiabatic process is process where no heat is transferred either to or from the system. In our case, the system is the gas inside of the container with the piston on the top. The change in internal energy of the system can be brought about by adding or subtracting heat or by work. The internal energy is the total energy of the system. We can say that it's the sum of potential and kinetic energies of our system. Now, for simplicity, we will assume that our gas is monoatomic, so the entire change in the internal energy goes into speeding or slowing down the gas atoms. The main conclusion of our discussion will also hold for polyatomic gases, but in case of polyatomic species, not all of the change in the internal energy goes into speeding or slowing the molecules. Part of it goes into changing the rotational excitation of the gas molecules, part of it goes into changing the vibrational excitations of the gas molecules. But our dull monatomic gas cannot have rotational excitations and doesn't have bonds vibrations because it doesn't have bonds. We said that the change in internal energy have heat and work component, and the signs are important. So let's look at these two examples. If a system releases energy as heat into its surroundings, the heat is written with a negative sign, and when the system acquires energy as heat from the surroundings, then the heat is written with a positive sign. And that's why the negative signs here. Work has a negative sign if the work is done by the system, like here in example 1, and it has a positive sign if the work is done on the system, like in example 2. In adiabatic process there is no heat transfer, so the change in heat is 0, and compression means that the work is done on the system, so the internal energy increases, and that increases average molecular kinetic energy, so the temperature of the gas increases. No heat exchange means that the walls provide perfect thermal insulation, which is really not achievable. From a molecular point of view, that means that collisions between the gas atoms and the walls of the container are perfectly elastic. If the collision is a perfect elastic collision, that means that upon collision, no kinetic energy is transferred to any other means of energy. The gas atom does not affect the lattice vibrations in a solid that makes the walls of the container or anything along these lines. Now we can also assume that the mass of the wall is much greater than the mass of the gas atom, so the wall stays fixed and the atom bounces back with the same kinetic energy. So how do they speed up? They speed up by collisions with the piston moving down. At every atomic impact, the moving piston transmits a certain impulse to the monoatomic gas. That increases kinetic energy and that increases the gas temperature. If you want to read some more, here are some papers that might be worth reading. And the final thing that I need to say is that the compression in an engine is approximately adiabatic, not because the walls of the cylinder are very good at thermal insulation, they're not really, but because there is not enough time for all the heat to escape. In other words, heat conduction through the walls is slow compared to the compression time. So the second main difference is how the ignition is brought about. Highly volatile petrol mixes with air efficiently. As a result, just a spark is sufficient to produce a smooth combustion. Now diesel do not mix well with air, so we need a different approach. In diesel engine, the piston goes up much more, the compression is much more than in petrol engines. Diesel engine compress the air to such temperatures that when diesel fuel is sprayed into the cylinder, the combustion will occur. Now let's analyze what will happen if we put petrol to diesel car and diesel to petrol car. Diesel to petrol car. What happens? Nothing. You will not be able to ignite because you will not be able to make that homogeneous air-fuel mixture. Now, what happens if we put petrol to diesel car? Well, it will detonate. It doesn't mean that your engine will explode into pieces. No, but engine in modern cars do around 2,000-3,000 RPM, rotations per minute. But in 4-stroke engine, every 4 cycles requires 2 rotations of the crankshaft. That gives about 1,000 combustions per minute. Or if you put petrol to diesel, that means 1,000 detonations per minute. And that puts your engine under lots of stress, which eventually will lead to damage. And I'm sure that you instinctively know what detonation is, but let's give some definition to it. Let's say we have a petrol engine, a spark plug ignites the fuel-air mixture, and the combustion propagates from the spark plug. What divides the burnt and unburned fuel is the flame front. When the flame front travels at the subsonic speed, the process is called deflagration. If the flame front travels at the supersonic speed, then the process is called detonation. Deflagration speed is usually below 100 meters per second and detonation around 1000 meters per second, although I found this book that says for hydrocarbons air mixture the values are more like 300 and 3000 meters per second respectively. And it might be interesting for you that it is the flame front where burning of the hydrocarbons mostly takes place, and thermal formation of nitrogen oxides takes place in the burned area because thermal nitrogen oxides formation is order of magnitude slower than oxidation of hydrocarbons. So coming back to the main topic, diesel not only can, but has to compress more, because the higher the compression, the higher the temperature, and diesel ignites solely due to the temperature in the cylinder. Static compression ratio is the ratio of the maximum to minimum volume in the cylinder, and I don't know how accurate the numbers are, but I found that petrol engines have compression ratios between 10:1 and 14:1, and diesel engines have ratios between 18:1 and 23:1. Now, that's one of the best things about diesel. The higher the compression ratios, the higher the thermal efficiency. What is thermal efficiency? It's a performance measure of the device that uses thermal energy. So I found this simplified diagram. We have energy input, in our case it will be energy from combustion of hydrocarbons. Some of that energy is transferred into useful work that moves the pistons, and some of the energy will be lost in the form of heat. So thermal energy will be between 1 and 0. 1 would mean that the device, in our case an engine, converts all the energy input into useful work, but 100% is never reached because that is against the law of thermodynamics. Anyway, this equation can be manipulated and we get this. The compression ratio is raised to the power of k-1, but what is important is that k-1 is just a positive number. So we want this term to be as small as possible so that we are as close to 1 as we can. When the compression ratio gets bigger, then 1/, gets smaller. Again, I'm not sure how precise the values are, but it seems that petrol engines' efficiency oscillates around 25%, whereas diesel around 35%. Although big diesel engines, for instance on ships, apparently can have efficiency almost up to 50%. Coming back to compression ratio, ideally we would like as high compression in petrol engines as possible, but compression ratio in petrol engine is limited by so-called knocking. So hopefully you could hear the metallic ping sound, and let's see what happens. So high compression means high temperature and pressure, and when the spark plug ignites the mixture, this further increases temperature and pressure. Caused by combustion pressure and induced heat, a second, spontaneous and almost parallel combustion in the mixture will occur. When both flame front hit, high-frequency pressure waves are produced, creating the characteristic metallic ping sound. So can anything be done to increase the compression in a petrol engine? Well, we can modify the fuel. There are various additives that can be used to make petrol more knock resistant. One of them was tetraethyl lead, TEL for short. Now, the problem is that lead is toxic. It was found that children were particularly sensitive to low-level ambient exposure to lead, which was linked, for instance, with low IQ and nerve damage. Lead neurotoxic effects were suspected since ancient times, so why lead? I'll point you to BBC article, Why Did We Use Leaded Petrol for So Long? And this article also seemed to be a good resource. The answer seems to be in this paragraph. GM stands for famous General Motors, and Standard Oil Company was an American oil producing, transporting, refining, and marketing company. It was the largest oil refiner in the world of its time. And just to appreciate some numbers, at its peak in the mid-1970s, leaded petrol released about 200,000 tons of lead into the atmosphere annually in both the US and Europe. I think no comment is needed. Another major reason why leaded petrol was finally forbidden in most of the countries was the fact that lead poisons, that is, deactivates catalytic converters. So as I said, eventually compounds like ethanol started to be used. Interestingly, the presence of extra oxygen from ethanol helps to minimize the products of incomplete combustion. So higher compression leads to higher in-cylinder temperature, and increasing temperature increases the rate of nitrogen oxides formation. So that's why it is diesel that used to be the most criticized for nitrogen oxides formation. Having said that, lots has been done to lower the nitrogen oxides emission. Take for instance EGR. EGR stands for exhaust gas recirculation. The idea is that part of the exhaust that leaves the engine is directed back to the engine. Why this reduces nitrogen oxides? Well, now the air in the engine is enriched with the product of combustion, like carbon dioxide and water vapor, and both of them have high heat capacity. What is heat capacity? It is defined as the amount of heat that when supplied to a given mass of material, it will produce a unit change in its temperature. So more water vapor and carbon dioxide means more heat is needed to raise the temperature of the gas mixture in the cylinder, and that lowers the peak temperature, which in turn slows down the rate of nitrogen oxides formation. So let's continue with differences between petrol and diesel. I already mentioned that petrol-air mixture is homogeneous, whereas when diesel fuel is injected into a diesel engine, the mixture is heterogeneous. There are areas with lumps of fuel which are not fully mixed with the air. A lot has been done to improve the mixing. The top of the cylinder rotates to swell the air in the cylinder. The fuel injection pressure has been increased to produce very small fuel droplets. Indeed, the pressure at which the diesel fuel is injected can exceed 2000 bar, which seems to be 30 times more than the pressure found in reactors for thermal cracking of crude oil. Heterogeneous mixture inside of the diesel cylinder leads to two important consequences. First, fuel-rich areas are prone to incomplete combustion. Locally, we have many molecules of fuel, but few molecules of oxygen. So to ensure as clean burning as possible, diesel operates with excess of oxygen. In contrast, in petrol engines, the amount of fuel and air is chosen so that fuel combustion uses pretty much all the oxygen available in the cylinder. We say that air-fuel mixture oscillates near stoichiometry, and we will see this is also to reduce emissions from petrol cars. Second consequence of heterogeneous air-fuel mixture is particulate matter. In spite of all the effort, oxygen delivery is not perfect and soot is created, which is not that big issue for petrol cars. It's interesting to notice that increase of temperature reduces particulate matter but increases nitrogen oxides formation. So scientists found themselves between a rock and a hard place, and only a design of DPF, diesel particulate filter, seems to bring some breakthrough.